Hello all, good evening. So it is 6 p.m. already, but nobody has joined yet. We'll wait for another few minutes and then we'll start the class. Hello, Mr. Prabhakar. Thank you for joining the class. Eager learners like you keep make the class
No, come on,
successful.
don't tell me.
Yeah, sure. Like, why not? Nobody else has joined, anyways. So, let's start the class then. I don't think there is any point to wait for others.
When somebody is ready to share the knowledge, why don't we take that?
Yeah, no problem. Yeah, so good evening and hello to all whoever is watching in YouTube. I would request you to pardon me if I look tired a little bit today. I had a long day for a factory visit and I'm just coming back. So, without any further ado, I would start the class today. I am Sharanya Banerjee. I am a PhD research scholar at IIT Delhi in the Department of Civil Engineering, and I have been giving this live interactive sessions for the course Matrix Methods, of Structure Analysis. So last week we were discussing about the week 4 problem, the basically this truss problem, stiffness method to solve the truss problem. And in that problem we went till mm, we almost completed the solution. We were already reached this point. Yes. We already reached this point where we have this equation pk equals to k u u okay, so the known load equals to the desired partition stiffness matrix into the unknown displacements. So we already discussed about this in the last class in quite some detail on how to partition the stiffness matrix. And then so from the last class I would just continue from that point and I would ask you whether you can follow. So from the last class we have already partitioned the stiffness matrix. We know the known forces, we know the unknown displacements. So now our next task would be to write the equation. So the equation for that would be like this. And now writing down their values, it would be 0 0 minus 3 minus 3 and AE. Now there is a big matrix here. I'll try to fit in over here. 0 0 2. If you all have the notes from last class, then you can correlate and check whether I am writing the right values or not. So this is the stiffness matrix and I don't have space to write the load matrix, sorry, unknown displacement. So it will be U5, U7, U3 and U4 in transpose. Okay, this kind of notation is okay, I guess. I am writing it as a row but it is a column vector. So these two are multiplied, this and this. So are we clear till this point? I guess we already got this point in the last class itself, right? So this equation is okay, right? Any confusion with this equation?
No, Mr. Karas. No,
No.
it's fine.
Okay. Yeah. So now we have four equations, four unknowns. We can solve the unknowns, or what we can do is we can um, find the u vector as a inverse of ku vector into the p vector. Okay, so this is u vector, this is pk vector. So with this I think everybody could find the answer. I am not going into the detailed calculation, I am leaving that to you. The answer would be, I am writing the final answer, and if you feel like, you can calculate this and check with your answers. So the final answer would be something like this: 8.847. So this is the answer for the displacement, unknown displacements. So we have already achieved what is the unknown displacements of the structure, of the truss kind of structure. Now I don't think there should be any problem in finding the unknown displacements. So now the next part would be how to find the unknown forces. So let's quickly recap what was the problem in hand. Our problem was this: we had the known forces over here, we had the unknown displacements at node numbers, which node? We had the unknown displacements at node number 3, 4, 7 and 5. 3, 4, 5 and 7. We have already achieved the answer for the unknown displacements. Now what are the unknown forces? The unknown forces in this truss kind of structure would be the reaction forces. So there are two reaction forces, 1 and 2, and there is one more and there are two other reaction forces from the roller supports, which are given as 3 and 8. So 1, 2, 3 and 8 are the unknown forces. Let us check whether this is unknown forces. Yes, so we can see in this vector that 1, 3, 1, 6, 7, 8. Let me check what is happening over here. Unknown forces will be 1, 2, 6 and 8. Sorry, 1, 2, 6 and 8. Yeah. So we have 1, 6, 2, 8. So we already have our load vector, unknown load vector partitioned at one side of the equation. So we have this P unknown. Now this P unknown would be multiplied with the K unknown into U unknown. So if we multiply P unknown, now if we try to find P unknown, we multiply K unknown into U unknown. So K unknown would be this one, minus 0.25, this vector basically. So if we multiply this vector with this U unknown, then we will get the P unknown values. Why we will get the P unknown values? Because the other displacement are 0, so the contribution from this K known part is 0, as we can see here in this equation, right?
Yes.
So now the unknown forces can be found easily, I guess. There is no problem to find the unknown forces. The unknown forces for this problem would be 2.977 minus 2.919, 1.085 minus 1.165. And what would be the order of the unknown forces? Order would be P1, P6, P2, P8. So you can kindly check whether these are the answers that would be received. So now we also have the unknown forces. Anything else we want to find out for this truss problem? We have got the unknown displacement, we have got the unknown forces. Anything else which we would like to know?
No, nothing. From this, I think we can easily find the member forces.
Yeah. So there is one more part, that is the finding out the member forces, which yeah, we can find out from this easily, but still I would just discuss it for the sake of the class. So So now we can find the member forces. I will just show you one example member force for member 1. For member 1, okay. So member 1 is aligned like this as far as I remember, and as far my notes in my copy are correct. U1, U2. Okay, what happened here? This is U3, U4. So basically for member forces we would like to calculate this force. This is the member force, right, which we would like to know. Now
Yes.
how we will know this member force? So it would be better if we go back to our original derivation for the force and stiffness matrix. Yeah, for the stiffness matrix. So original derivation was like this. Excuse me. So initially we had the equation of the member forces as this. Okay, is my blue color box visible? So this was the initial
Yes.
equation
Yes.
for the member forces, like, right,
Yes.
where
Yes.
everything was in local coordinate system, right? So now we
Okay.
just want to find the left side, find the member forces, but we have the global coordinate system displacements. So what we do, we convert the displacement into the local coordinate system. Sorry. We convert the local coordinate system displacement into global coordinate system. So how to convert local to global? This blue box will give us the local coordinate system displacement in terms of the global coordinate system displacement. So basically what we want to do here is we want to find the answer of the member forces as, so now basically the member forces F1 and F2 would become AE by L 1 minus 1 minus 1 1 into transformation matrix into the unknown displacements, into the displacements of the considered member. The displacement of the considered member are u1, u2, u3, u4, right? This equation is acceptable to all? I think so, right? This equation is correct, right? I think this equation is acceptable. Now let us check what was the member, what was the transformation matrix for member 1. Transformation matrix was 0 0.8, 0 0.6, 0, 0, 0 0.8, 0 0.6. So we'll write the transformation matrix over here. 0 0.8, 0 0.6, 0, 0, 0, 0, 0 0.8, 0 0.6. Now everything we know, u1, u2, u3, u4. What is u1? u1 equals to 0, u2 equals to 0, u3 equals to how much, and u4 equals to how much. We can find, we have written the displacement vector. Where is the displacement vector? These are the unknown displacements in the order of u5, u7, u3, u4. So the last two. So these two values. So u3 would be 1 by AE into minus 17.943, and u4 would be 1 by AE into 8.847, right? So now we know u1, u2, u3, u4. We know AE by L. We know this 1 minus 1 minus 1 1. We know T. We can easily find F1 and F2. And if we want to make our jobs easy, we can only find one, because the other one would be the negative of that. But still we need to check whether our uh, answer is positive or negative. So basically f1 and f2 could be whatever this matrix could be, you will find f1 and f2 like this. So basically without finding f1 and f2 we can also only find f1. How much would be f1? F1 would be the first row of that matrix. Fine. So the first row of that matrix, if we find, and if we find the answer to be positive, then what is our force? Compressive or tensile? What is
Is
our force?
tension.
No, it is compression. So here you see these are the joint forces on the member, right?
Exactly, compression. Yes,
Yeah,
compression.
yeah. So these are F1 and this is F2. So it is actually compressive force. Uh, so actually F2 is not like this. F2 will be like this after we. This is not F1 and F2. This is F. Now F equals to F1 equals to minus F2. When we take the stiffness matrix, we consider both the forces in this direction. You might remember. So then we call this one is F1, this one is F2. But this F would be F1 and equals to minus F2. So the answer of this F1 for member 1 would be 1.808, and this would be positive. So F1 is so not F1, let me write F is 1.808 compression for member 1. This is the answer. So so now we know how to find the how to find the unknown displacements, how to find the unknown forces, and how to find the unknown member forces. So this, I guess, completes our truss problem. Any questions from this part? So with this I will close the truss problem now. Any questions?
No.
No, right? Okay. So we also have Mr. Sudhakaran attending the meeting. So Mr. Sudhakaran, you are also free to unmute yourself and express your views, whether you have any questions or not. And irrespective of that, let's move on. So this is the complete truss problem. So last week I had already uploaded this document in the drive for your reference, but this week I will replace the previous document with this one because this has the complete problem. Okay, so I will not add a separate document, I will replace it. So this completes your truss problem. Now moving on to week 5. In week 5, basically what the in the lectures we have observed that the beam problem was considered and it was solved uh, in the class. Yeah, Mr. Sudhakaran, are you trying to say something?
Nothing, sir.
Okay, okay. So do you have any questions? No, right?
No, sir, I can understand.
Okay, okay. Very nice, very nice. Thank you for attending. Um, so now in today's class we'll basically take up the beam problem from one previous year's assignment and solve it again step by step as we have done for the truss problem. But before that, there was a request in the last class on eigenvalues and eigenvectors, right, Mr. Prabhakar?
Yes, yes.
Yes. So I will discuss not elaborately on this, I'll discuss slightly on this and then we'll start the beam problem. Before I discuss, I just remembered one more thing from last class. Now, in the last class, there was also one question from Mr. Prabhakar that which degrees of freedom should we choose while
Numbering of the nodes.
while numbering the numbering the degrees of freedom so that we don't need to partition. So after solving the problem, I don't think the question still persists, but still like it is very evident that you have to choose the unknown degrees of freedom first to keep them together in the unknown displacement vector and in the unknown force vector, and subsequently you can directly partition your stiffness matrix. So in this case, if you could have numbered these equations like this, say 1, say 2, I hope my red color ink is visible, 3, and here 4. So if you could have numbered it like this, 1 2 3 4, then you could have receive then you didn't have to then you don't need to like do the row and column operations to find the correct way to partition the stiffness matrix. So I think this is quite clear. So
So
uh,
whatever the
yeah,
unknowns are there, we
yeah.
can number them serially, right? So
Yes, yes, yes.
whether it is in order or in a random fashion, say take
Doesn't
for
matter.
example this A B C D node, I can give U1 U2 and A and B U3 U4 or D U5. I mean, it
Yeah,
doesn't
yeah,
matter,
yeah.
right?
Yeah, doesn't matter.
So
Nothing
unknown should
matters.
be in
Yeah.
a order. Unknown should be in order. That's it. I mean,
Uh,
irrespective of its joint number.
yeah, yeah, yeah. Unknown. You can also like do like this. Say, mm, okay. So you can also mark this 1, this 2, and this 3, this 4, and the rest as 5, 6, 7, 8. Like you could also choose to keep the unknowns at the bottom and the knowns at the top. Again, in that case also you don't need to do any operations. You already have the matrix. So
Okay.
basically what I'm trying to convey in through this message is like when we see a stiffness matrix, I would like you all to visualize this as a system of equations, right? So these are nothing but a system of equations. Big stiffness matrices, they may be 8 by 8 or 9 by 9 or anything, but they are at the end a system of equations. So whatever if you want to solve the system of equations, if you want here, why did you need to do the row operations and column operations to partition the matrix? Because it was not visible to us that which is k11, which is k12, which is k21, which is k22, right? Or kku, kuu, k kk, kuk, kuu, and kuk. So whichever is which, it was not visible to us. So that is why we need to do the operations and do like this. Okay. But if you could group them together, there is no need like there is no need to select that the first four would be the unknown displacements or the first four would be the known displacements. Anything you can do, but as long as you can group and you can quickly solve, it is better for you. That's all. Apart from that, there is no significance of the numbering. Only thing is you need to be consistent with the numbering. Like in the last class also, I emphasized a lot on the writing these joint numbers on the stiffness matrix. So whenever you are solving a problem, I would encourage you to write the joint numbers on the stiffness matrix. Each time if you write the joint numbers, then the confusions will be less. Like you already know that which joint numbering you are following. Okay. So it is up to you, but if it is grouped together, then you don't have to do any row operations or column operations to get the smaller matrices, partitioned matrices, right? Is that understood?
Yep, it's clear.
Okay.
Yep.
Yeah. Yeah. But like I would urge you all to like visualize the stiffness matrix as a system of linear equations, because it is nothing greater than a system of linear equations. So because the reason is like we are very much accustomed to linear equations. If we see ax plus b, y plus c, z equals to something d, and then we are very accustomed. Even in the last class, I would like to again touch a little bit upon that. Even in the last class, when we are having some problems on understanding how to do the row operations or column operations, we broke it down to a system of linear equations. So if we see the matrices as a system of linear equations, then things will be a lot more clear, and like you would not like I would suggest that except like blindly doing matrix inverse and finding the values of the unknowns, if you could visualize that we are doing the inverse and how it is coming through the system of linear equations, it would be better. Anyways, so moving on. So now, eigenvalues and eigenvectors. I actually read up a little bit on this topic, means, and I would try to explain about this. But the fact is, like, eigenvalues and eigenvectors is a very deep subject, very deep topic in mathematics, right? In linear algebra. So, but I don't see the need for this class to understand every detail of that mathematics, because it is no way related to this class and maybe not even applicable to any method in civil engineering as a whole. Even if you do dynamic analysis where you find the eigenvalues and eigenvectors as the modal frequencies and mode shapes respectively, even then a very deep knowledge on what is eigenvalues and how it is coming is not required, but the basic knowledge, that is always required. So I would discuss in detail about the basic, but I will not go into the mathematics. If you are interested to go into the mathematics, like, there are a lot of things like how to take the vector field and then transform it to another field and those kind of
It's enough
mathematics.
if it is up. I mean, where it is applicable in civil. I mean, that much information is enough. I mean,
Yeah,
students.
yeah, yeah, yeah.
Mainly in the
I
dynamics. If I read the code,
Yes, yes.
even in that 1893, they'll call out these eigenvalues, and I mean, we'll get
Oh,
confused.
okay,
What?
okay. Yes, yes.
Why
No,
they
no,
are
no.
calling it as?
That
I mean,
that
that's
part
the.
would be absolutely clear, and since you have pointed out that part, maybe I can discuss a little bit further on the dynamics issue also in terms of whatever we'll discuss first on eigenvalues. So, uh, so basically, as in the last class also, I was discussing one thing, that what is the eigenvalue problem, right? So this is again a system of linear equations. Okay, system of linear equations. Now this is a matrix n cross 1 n cross n, sorry. This is a vector n cross 1. This is a scalar. I am writing 1 cross 1 means it is a scalar. A scalar means just a single value, nothing else. And this is again the same vector x n cross 1. Okay, so now again this will represent a system of linear equations, right? Okay, I'll break it down to a, say, simple example, very simple example. Say 1 minus 1 minus 1 1, x1 x2 equals to lambda. Lambda may be any value, equals to x1 x2. This is a system of linear equations. What does this system of linear equation mean? This system of linear equation basically means x1 minus x2 equals to lambda x1 and minus x1 plus x2 equals to lambda x2. This is the original system of linear equations. Okay, so any this kind of system of linear equation, now this is a unique system of linear equation. Can we agree with that? Like, what it is saying is that if you multiply a matrix with a certain vector, it could be equal to a scalar product of that vector. Okay, so this is a uh, like unique. I would fear to use the term unique, because unique also has some significance in matrix algebra, but I would say that this is a very uncommon type of system of linear equations. This is not common. Okay, so this is a special system of linear equation, and this is called the eigenvalue problem. Okay, so whenever you have a system of linear equation of this caliber, where you have ax equals to lambda x, where a is a matrix and lambda is a vector, lambda is a scalar, and x is your vector, this is called the eigenvalue problem. Now why do we like when we have a system of linear equations like this, say you have a system of linear equation like this, a x equals to b, okay, so what we basically do is we solve for x equals to a inverse of b, right? This is what we do. This is what we also did in the stiffness method problem, okay? But here you can see one very important observation is that there is x on both sides. If we just transform this to another form, say if we just write it in another form, we have a minus lambda I, okay, x equals to 0, okay. So this original system of linear equation can be transformed to this system. Do we agree? We just brought the lambda x part to this left hand side. We took x as common, and we found a new vector, and we found a new matrix. This is a new matrix. Okay.
I is the identity matrix.
I is identity matrix. Yes. Okay. So now, can you quickly give me a solution of this system of linear equation? Very quickly. This is, say, this is a product of two things equals to 0. So what would be the solution of this equation? One possible solution would be x equals to 0, right? If x equals to 0 for any matrix A and any vector, any scalar lambda, this equation holds, right? Do you
Yes.
agree with this?
Mm-hmm.
Yes. But we are saying x cannot be 0. Like,
Yes.
what will happen? Say this is the system of linear equation, and we want to find some solution for x. Okay, we cannot tell that x equals to 0. We want some solution for x. So what would be the solution? This has to be the I'm sorry. This has to be this has to be 0, and what of that? The determinant of this matrix has to be 0. Okay, is this understood? So if the determinant of this matrix is 0, then we'll have some solution for x. Fine.
Okay.
Okay, so this specific kind of system of linear equation, solution of system of a linear equation, is called the eigenvalue problem. And this lambda this lambda this lambda will have many values. Lambda equals to many values. How many values? N number of values. Okay, this lambda will have n number of values. Why it will have n number of values, I will explain just after this. So this lambda will have n number of values, and for n number of values this determinant would be 0. So let's solve this problem. If we have, say, okay, let's take this example itself, what we took earlier. Okay, so now if we want to say determinant of 1 minus 1 minus 1 1 minus lambda 1 0 0 1 equals to 0. Okay, fine. So now what would be the answer for this? This will be determinant of 1 minus lambda. Please stop me if you don't understand any of the calculation. Okay, equals to 0. What is the determinant of this matrix? 1 minus lambda, 1 minus lambda minus 1 equals to 0. So this equation, what is the order of this equation?
Second degree.
Second degree. Why second degree?
Square.
Because
1
the
minus lambda square.
matrix
2
was
by 2 matrix,
2 by
2 by
2.
2, and
Yeah.
it is 1 minus lambda square. It is.
Yes, 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 yes. So any nth order matrix would have the degree of this equation, order of this equation as n. Okay. So now if we solve this problem, we have n values of lambda for which you have this determinant to be 0. Fine? Fine till now? So this
Yes.
is a unique procedure for solving a system of linear equations which we did not encounter earlier. By simply by our what to say, hmm, simply by whatever solution we used to approach earlier, first answer for us would be that x equals to 0. Okay, if something equals to 0 without any constants, x equals to 0, right? But now we are telling that x is not equals to 0. Find me some solution for x in this present scenario. And in this present scenario, a solution for x would be when these lambda will take up this n values. And now comes the next important part. So now you have different cases. Minus lambda 1, lambda I say. Now we are converted to this kind of situation. Okay, the system of linear equation which we had, it is converted to this kind of system where for each lambda you will get a solution for x. Okay.
Yes.
Yes. So this pair of lambda I comma xi, this is called the eigenvalue. This is called the eigenvector. Okay. Now a
Why
very
it is xi? It
yeah,
should be x, right? Why it is xi here?
xi because for
Only
every,
lambda I got to lambda 1, 2, 3, correct? Because
yeah, lambda is lambda 1 2
x
3.
remains same. X remains the same, right?
No, for each lambda you will get a different x. For every lambda you will get a different x.
Okay, to become make it as 0. Agreed. Yep.
Yes. For every lambda, there will be pair of lambda I and xi. For every lambda, you will get a different x. So you have n values of lambda, right? So when you put the value of lambda one time, you will get 1x. If you put a different value of lambda, you will get a different x. So lambda I and xi are in pairs. Okay. Yeah. So it is clear now. It is clear, right?
Yes, sir, Mr. Paras.
Yes. Okay. Very good. Very good. So now we have almost covered the basic part. Just one more question.
What is that
So
eigenvalue? When vector is that variable, different
vector is
variable.
the whole vector xi, like it will have
Okay.
n number of values. This is a vector.
Okay.
But this lambda is a value. You'll get only one value of lambda. Like you'll get n values of lambda, and you'll get n vectors of x. Okay. So this is a scalar, lambda I eigenvalues, and this is a vector. So eigenvector. Okay. So naming is also clear. Now a very
So what
interesting
you're
question.
okay? Let us be. What you're telling is if for one lambda 1,
Yes.
there will be x1, x2 for each, correct?
Yes.
Because
Yes.
it's for 2 by 2, correct?
Yes.
For
Yes.
lambda 2, again we'll have a x1, x2. So
Yeah.
those will be different. Okay, got it.
Different.
Thanks.
Yes. And for this very simple problem also you can solve and you can check this will be the case. But I think you can also visualize that this will be the case, right?
Yes.
Yes. So now a very interesting question. Say this is xi. So you have found this xi. So what if you multiply this xi into 2? 2xi. Okay, you are using the same lambda I, you are using 2xi. Okay, so this equation still holds because right hand side is 0. This equation still holds, right?
Yes.
Yes. So now, so now, so can we say that this could be xi or 2xi or 3xi or anything xi? Yes, right? This could be any scalar multiple of xi.
Difficult to visualize.
Difficult. Okay, okay. So I am enjoying this part. Let's solve this equation. 1 minus 2 lambda uh, plus lambda square minus 1 equals to 0. So this 1 goes away. Okay, we have got a lambda equals to 0. Very good. Lambda equals to 0 or 2. Do you agree? Yes. Lambda equals to 0 or 2. These are the two eigenvalues. Very good. Now, these are the two eigenvalues. Now what happens is we put the two eigenvalues in the two solutions. So we have a 1 minus 1 minus 1 1 minus 0 I. So basically this is this one. This is one case. We have 1 minus 1 minus 1 1 minus 2i. Okay, so this will give yeah, we are coming to a very interesting point now. So this will give 1 minus 1 minus 1 1. This will be minus 1 minus 1. Okay, this was minus 1 minus 1. Okay, so now we have equation x1 x2 equals to 0. We have equation x1 x2 equals to 0. This part is clear, whatever I have written?
Yes, yes, yes.
Yes. Okay. So how do you solve x1 x2 from here? Right hand side is 0. You do inverse and you get x1 x2 equals to 0, but we already know x1 x2 is not 0. So here the interesting part is we assume, let's assume x1 1 equals to 1. Then we get a value of x2 1. Okay, if we assume x1 1 equals to 1, then what is x2 1? x2 1 is also equals to 1, I guess. Yes, x2 1 is also equals to 1. If we assume x1 2 equals to 1, what is x2 1? x2 1 x2 2 equals to minus 1. This part is clear. Let's see. Is this clear?
Assumptions part is now why we are assuming it is x1 1.
Yeah, let us
Okay, we're
assume.
assuming one value or finding the other
Yeah, assuming one
to
value,
make it
finding the
0.
other. Assuming one
Okay.
value, finding the other. Okay.
Yes.
So this is a set of non-zero unique non-zero vector of x1 and x2, right? Corresponding to lambda 1 and lambda 2.
Correct.
Yes. So now instead of assuming 1, if you could assume 2, you will get the answer as 2.
Okay, got it.
Right? So any scalar multiple of this vector is also the same eigenvector. So that is why there comes the importance of the concept of amplitude and shape. Okay. So these eigenvalues, the amplitude of the eigenvalues we cannot trust. Like their amplitude has no meaning. They can be 1, 2, 3, 4, anything. But the shape is very important. Like what is the shape? Like if this is 1, then this will be 1. If this is 1, then this will be minus 1. This gives us very important information about what is the shape of the vector. Okay. Shape of the vector means if you plot this vector, say if you plot this vector like this, x1, say x1 equals to 1, um, uh, how to plot, say this is x1, this is x2, say this is plus 1, this is plus 1, this is one shape. Now this is plus 1, this is 0 1, this is plus 1 minus 1 0 1, this is plus 1, this is minus 1. I'll try to draw a straight line. Yeah. Assume this line is straight. Okay. Anyway, so now are we getting two different shapes of the vector? This is
Yes.
this is okay. So now this shape we can trust. These values 1, minus 1, 2 we cannot trust. This can be anything. Okay. But the shape we can trust. This is a very important information on this vector. So we had a like dead end where we cannot solve a vector. We were saying that this vector is actually 0, but we told no, let's find a non-zero solution of this vector, and we found a very important information on the shape of the vector. Okay. So this is basically the eigenvalue problem, where we get a pairs of eigenvalues and eigenvectors. Now is this problem clear, that how to calculate and how to do these things and these things?
Yes, at least you got the concept, at least. Yes.
Yes. So now, very interestingly, we will jump into structural dynamics. Say very basic things we'll start with. Can we write the equation of motion for this kind of system in structural dynamics? I guess it would be difficult because, but then this is not a class of dynamics also. I will give you the equation. Okay. You can recall the equation. Can you recall this equation of motion? This is a free vibration of 2 degree of freedom system. Can you recall this?
Yes.
Yes. So now this is a matrix K, which is basically nothing but the A matrix. Okay. And this is a matrix. So okay. Okay. Still, I think we need to do some steps before we can tell that this is an eigenvalue problem. Now if we consider the motion of this, if we consider the motion of this vector as x equals to a sine omega t. Okay, in dynamics we do these things.
Yes.
So what would be x double dot? X double dot is double derivative of this. This would be minus a omega square sine omega t. Agreed?
Yes.
Okay, very good. Now this m1, if we just divide m1, if we just make m1 as 1 and divide this by m1, divide this by m1, agreed? Similarly, if we make this one, divide this by m2, divide this by m2. Again, a system of linear equations, if you just divide m1 and just divide m2, this is what happens. Okay?
Why dividing M1, M2? What is that step? I didn't understand.
In the first equation, like you have two equations, one say, you can see the two equations, 1 and 2. In the first equation, I am dividing the whole equation by m1 and I am dividing the whole second equation by m2. You just sink in this step, you will understand in the next step why I did that. But this is possible, like you just understand that this is possible.
Mhm.
Okay, if this is possible, then let us assume this to be a. Okay, we like a very much. Let us assume this to be a. Now I would say this is nothing but comments on this, please. This first equation is nothing but this, I would say. The k by m matrix that we have considered as a into x, and we have put the values of x1 double dot and x2 double dot. So that will make us minus omega square x, minus omega square x1 sine omega t, minus omega square a sine omega a1 sine omega t, and minus minus omega square a2 sine omega t. Okay, so that will be omega square into, this is now identity matrix, this is I. So this form of the equation is okay.
Yep.
Yes. So now this is a eigenvalue problem. Now we know this, right?
Mm-hmm.
So what are the eigenvalues and what are the eigenvectors?
Eigenvalue is omega square, that is that
Omega
frequency.
squares are eigenvalues. Anywhere you see eigenvalues, that is omega square. That's all.
That is frequency, basically.
Basically the square of the frequency. That's all.
And the vectors, displacements.
Yeah. And what are the eigenvectors? That is the
Displacement.
mode shapes, not displacement,
Okay,
mode
okay,
shapes.
okay.
Yeah. Why mode shapes? Because the amplitude doesn't have any significance. And how do you correlate that with physical thing? So so
For different vibration, what is its, how that shape of that vibration, of that
yes,
mass, I
yes.
mean, basically how it is
Yes, this
vibrating.
is mode shape. Now I would try to make you understand the physical significance of it. So say you have a say you have a what do you have? You have a steel ruler, say, okay, and you have a large mass on the top of the steel ruler. Can we imagine? Say something like this,
Yeah, inverted pendulum. Okay.
inverted pendulum, okay, something like this, okay. So why a big mass on the top? Just to ignore the variation of mass of the steel ruler, okay. Assume that the steel ruler has no mass. So the steel ruler is massless, but it will give you a stiffness in the horizontal direction, and this is mass, okay. So now how do you observe free vibration here? If you just have this steel ruler and the mass, you can see that this is vibrating. Will that vibrate?
Yes, it will vibrate.
If you just do nothing, you just hold a steel ruler with a mass at the top, will it vibrate?
I mean, till you apply some external load,
Yes,
it
yes.
will not
Like you
vibrate.
have to do something for
Yes.
it to vibrate. It will not vibrate initially. So so now what is free vibration? Can you define what is free vibration?
I mean, its amplitude remains same for. I mean, it won't stop or
Okay.
whatever that.
Yes, yes. But to what actually happens is if you just have a system, it will not freely vibrate. To make it freely vibrate, you have to displace the system a little bit. Say you have to, oh sorry. Say you have to displace the system a little bit and then just leave it. Just don't give any force to it. Okay. You have to displace the system a little bit. This is your initial displacement and then you leave it. Then it will vibrate on its own, right? That we
Agreed.
can
Agreed.
visualize.
Yes.
Yes, yes. So like if we displace the system a little bit and then it will vibrate on its own, that we can understand. It will not vibrate on its own if we do nothing, okay, but we have to do something. So that something could be like you can that something could be various things, like you can give it some acceleration. How do you give it some acceleration? You take a hammer, you just hit it once, you have given it some acceleration. How? Or you can give it some displacement, so you can hold it, displace it to some position, leave it, then it will vibrate on its own. Or you can give it some velocity, so you can just take it, hold it and move it fast and leave it, then it will vibrate freely. Okay. Now assuming everything is ideal, there is no damping, there is nothing, the stiffness is ideal, it is not changing anything, the mass of the ruler is zero, everything, then this will only have one mode of vibration. Why? Because this is a 1 degree of freedom system, right? Okay.
Agreed. Agreed. Yes.
Yes. So now, what happens is, now this will only, under free vibration, this will only have one natural frequency of vibration. Okay. Agreed.
Mm-hmm.
So now what would be the amplitude of vibration then? You have
It
no
can be
I
anything. It can be anything.
It can be anything, like you can displace it 1 centimeter, you can displace it 2 centimeter, you can displace it 5 centimeter. The vibration frequency would be same, it will vibrate at the same pace, but you don't have any idea on the amplitude, but you definitely know that what is its frequency and what will be its shape of vibration. Okay. Are we clear with this?
Yeah. If it is damped vibration, I can understand. It will. It is not same, but for free vibration, yes.
For
It
damped,
can have a
you
much.
just forget about
Yeah.
damped for the
Yes.
time.
Yes.
Yeah.
I mean, for different amplitude, yes, I agree with you. It will.
Yes, yes, yes.
Frequency will be same. Yes.
Yes, yes. So now how will you find the amplitude? You have to find the amplitude by the initial displacement and initial velocity and those things. But that is not included in this equation, in this eigenvalue problem. Okay. So this is the basic of like I mode shapes and natural frequency. And you would be amazed that for any damped vibration, multi-degree of freedom structure, multi-story structure, bridge, anything, damped, undamped, anything, we use this concept. We use this equation of motion. We find the natural frequencies through this process.
So eigenvalue for a, I mean, for different eigenvector, there will be a same eigenvalue. Is that what, I mean, how are we?
Yes, so
Same.
again, like coming back, like there will be pairs of eigenvalues and eigenvectors. So there will be pairs, like for there will be different frequencies. So we have, if it is a multi-story building or a multi-degree of freedom structure, there will be first frequency, second frequency, third frequency, like this. And for each frequency there will be different mode shapes. Okay. So if we yeah, if I could just explain over here. So let's
But
take.
that mode shape is constant for given eigenvalue, right? For given frequency.
Okay, I'll just show you. This is a 4 degree of freedom system. Agreed? Yes.
Yes.
Okay. You through this
Mr. Banerjee, I
discuss.
think we are taking others' time. I think we can go to that beam problem and then probably next week again further continue on this. I don't want to
Uh,
waste others'
I
time.
think we can just quickly finish. Like we have come to the
Okay,
end of
okay.
this point that I'm trying to make. um, okay. So for this 4 degree of freedom system, this will be omega 1 comma x1, omega 2 comma x2, omega 3 comma x3, omega 4 comma x4. And this I am not saying this as like this could be, this will be, like this is the answer. Okay, so there is a very good physical significance of this. Like the first natural frequency is the most dominant natural frequency, right? So if you take a scale, if you take only the steel ruler without the mass at the top, and if you displace it by a little bit, by a little, and you see the free vibration, it will always vibrate as a whole, the steel scale, right? It will always vibrate like this. Okay, now there would be second frequency also where it may vibrate like this. You can see some waves flowing through this, and as the frequency increases the waves will be more. Okay, so if it is omega 1, it will cut the neutral axis 0 times. If it is omega 2, it will cut the neutral axis 1 times. If it is omega 3, it will cut the neutral axis 2 times. It is omega 4, so basically n minus 1 times it will cut the neutral axis. Okay, so this is basically how we find the different mode shapes and the different natural frequencies of a system. I hope this makes it quite relatable on how we do dynamics with eigenvalue problem. Is it okay?
Yeah, I think probably we have to go back to some textbook and we have to read that now. So probably something may.
Yeah.
No, okay, fine.
and
Thanks.
and if you have any specific questions on this, again I'll be happy to discuss again. No problem in that. So
Sure.
so this was all the basic information about eigenvalues and eigenvectors, and also we have seen what is the physical significance for a dynamic system. Okay, now getting more into depth will serve no purpose for us as civil engineers or even as
Agreed.
mechanical
Agreed.
engineers. So
Agreed.
I would not discuss the numerous ways how to solve the eigenvalues and this thing, that thing. We will not go into the mathematics. You can take any linear algebra book of mathematics and you can see that. But there are numerous properties of eigenvalues. Okay, so the different properties of eigenvalues, can I okay, I think I'll have to write this, I'll write in the last page. Okay, please find it in this way. I didn't count in the um, example problem while calculating the blank sheets required. Anyways, so there are different properties of eigenvalues. I will only list a few properties of eigenvalues. One of the property is trace of the matrix A will give you the summation of the different eigenvalues. Okay, this is a property. This property has proof, but we don't need the proof. We are happy with only the property. Next is the determinant of the determinant of the matrix A will give you the will give you the product of the eigenvalues. Very interesting property, quickly relatable. We had the eigenvalues here 0 and 2. Why it is if it is 0 and 2, and what is the determinant of this matrix A? 1 minus minus 1, determinant is 0. The determinant of this matrix A is 0. That is the reason one of the eigenvalues is 0. Like, without even solving the eigenvalue problem, we could have mentioned that one of the eigenvalues would be 0. Okay, so when the first eigenvalue came out to be 0, I was not surprised, because I knew that okay, the determinant is 0. Fine. Then next property is eigenvalues of a to the kth power would be this. Okay, these are all properties. These have some proofs which don't have enough meaning in our applied knowledge. Okay, similarly, inverse of A will have 1 by I lambda I. Okay, so there are numerous properties like this. Most important property for which our whole discussion started is that eigenvalues of positive definite and negative definite and semi positive definite, semi negative definite. Can you guess? I think there is no, like, this would be a very easy guess. This would be positive, this would be negative, this would be 0 comma positive, that is non-negative, and this would be 0 comma negative, that is non-positive. Okay, so these are properties of eigenvalues. So now our last day this discussion came up from the question that whether the eigenvalues of a positive definite matrix of the Cholesky matrix, I guess, which matrix? I guess it was given that the positive definite matrix eigenvalues would be positive. That was one option, and that is coming from these properties of eigenvalues. So this part you have to just know. Like, I don't recommend you to go through the proof. Okay, so that part is clear. Now we'll close the discussion on eigenvalues. Everything is clear? Just a quick yes.
Yes.
Okay.
We need to read, of course, but okay. To start reading something, okay, this much is enough. Yeah.
Okay. If that is enough, then we move on to the next week's problem, the week 5 problem. So no worries, we have 50 minutes left, and okay, so we have 50 minutes left, and then we can we can discuss the solution of the problem, and how much we will achieve. After that we will continue in the next class. Okay, no problem with that. So this week we had the beam problem, right? The stiffness method, stiffness method to solve beams. Okay, so now our question in hand is, consider the following beam. The questions that follow, we don't worry about the question, we'll just solve it thoroughly. So this is a given beam. We can see this is a propped cantilever beam with two props, two vertical supports, and this is these are the different loading systems on the beam, right? That is clear. So now the first thing that we want to do here is, okay, in beam problem, before we start, we have we have numbered the what to say, we have numbered the degrees of freedom in this order. This is one. Okay, I will not destroy the figure. All the time I usually destroy the figure. So this is the beam in hand. Okay, we have the degrees of freedom like this. Okay, I will not do like this. We have the beam in hand. Let's say we have the beam in hand like so. The beam in hand like this. We have A, B, C points like this. Okay. We have different degrees of freedom. Why I am drawing only 2 degrees of freedom? Because this is a beam problem. So we will neglect the axial deformation of the beam. So we have only one vertical deformation and one rotation of the beam. I hope that is clear. If that is clear, so how are we numbering this? We are numbering this as, this is 1, this is 2, this is 3, then we are coming back like 4, 5, 6. This is the order in which we have numbered this beam. Like, why did we decide this order to number this beam? Can you guess?
To keep all unknowns in point.
Exactly. So that was the point. So to keep all the unknown displacements at the beginning of the displacement vector, we have taken this order of the beam of the degrees of freedom. Now we tell that this is member number 1, this is member number 2, and we solve the beam problem. Fortunately, beam problem is not so big, not so tedious, because there is no concept of transformation matrix. There is only one matrix in the beam problem, and that is the stiffness matrix. Now, why there is no transformation, I think that is clear, right? Like,
Yes, because it is
yes,
same. Global axis, local axis is same. So
exactly. There is only one line of beam that is going. There is no members moving out here and there. Okay, so the global axis and local axis is same. So if we have a beam, say like this, with degrees of freedom 1, 2. Okay, I did a mistake. 1, 2, 3, 4. These are the degrees of freedom of a beam member like this. We call it M. What is the stiffness matrix? This is the stiffness matrix. I have saved my work by copying it earlier. So regarding the derivation of the stiffness matrix, I think it was not discussed in like, the derivation was already obtained from our previous courses, right? The structure analysis 1 course. So the derivation was not done explicitly in the lectures, but I think you may recall that we have done the derivation in some other discussions
exactly.
in class,
Yes,
right?
yes, yes,
Okay.
yes.
So no problem. So now we know this is the stiffness matrix of the beam. So we'll directly go on to solve the beam. This is a very simple problem. First of all, what I would like to know is that what is the degree of static indeterminacy and what is the degree of kinematic indeterminacy. Let's start with kinematic indeterminacy. Very simple. What is the degree of kinematic indeterminacy?
Two.
2. Yes, the kinematic indeterminacy 2, and that is 1 and 2. So like, we already have the displacement vector u4, u5, u6. So it seems like the displacements are becoming smaller as they are increasing in number. Anyways, so this is the u unknown and u known. Okay, so there are two uh, uh, two degree of indeterminacy is 2. Very nice. What is the degree of static indeterminacy in this case? Very
2.
quickly. Again 2. This is a prop cantilever beam with two external supports like this. So static indeterminacy is also 2. Very good. No more time needed on this. Directly moving on to the solution of the problem. Now let's start with member 1. For member 1, okay, we have the member 1 like this. We have the okay, I will just write it down and you all will correlate. Okay, is this okay? These are the degrees of freedom for the different members. Is
Yes.
okay? Okay. So what is L? L is 6 meter for member 1. L equals to 6 meter. So let's find the value of 12 Vi by L cube. I hope I don't need to explain why we are finding the value of 12 Vi by L cube. So 12 into EI. Okay, what is EI? EI is constant, so we keep it as EI, no problem at all. Okay. So 12 by 6 cube, how much is that? The answer is EI by 18. Okay. Now let's move on to what is the value of 6 EI by L cube. 6 EI by L square, not L cube. 6 EI by L square, 6 EI by 6 square. How much is that? 1 by 6 EI. But since we have already got a dividing factor of 18, let's write in terms of 18 itself. 6 EI by L square equals to 3 EI by 18. Agreed? Yes. Okay, I'll just move fast in this because there is nothing very mm, what to say, non-understandable here. The most important parts come most important part comes along in the deciding of the force vector. Before that it's very straightforward. So these are the different values of the stiffness matrix. So what is the stiffness matrix for the first element? We will write the stiffness matrix. Okay, first we will write EI by 18 outside. We have taken that outside. Please check the stiffness matrix and comment that if I am doing anything wrong. Okay, most important part, what are the degrees of freedom? 5 2. Okay, P6 P3 P5 P2 1 equals to K1 U6. Please tell if there is any problem with this. I guess not. We have the degrees of freedom as 6 3 5 2. We have calculated the values of the different elements of stiffness matrix. We have formed the stiffness matrix for element 1 and we have numbered the stiffness matrix as we have in the global system. Okay, so just just to give you a reminder that we are working with 6 3 5 2 degrees of freedom, I have reiterated this equation of motion. Member 1 is clear? Yes. Okay, I guess it is clear. For member 2, let's move on to member 2. What are the degrees of freedom for member 2? 5, 2, 4, 1. Very nice. So again we'll calculate what are the different values. L equals to 3 in this case. Quite good. Next week's problem is a little bit simpler, I guess, in terms of the geometry. Again we are keeping a dividing factor of 18 because later on we'll combine the two stiffness matrices, so we just want EI by 18 outside. Okay, we don't want to like use our precious brain cells on this thing, on finding the different dividing factors. These values I would urge you to check, but I don't think I would have checked if I would have attended this class. But anyways, like you will be solving a similar problem for your assignment also, so it would help. Okay, the most important part is the for one. Okay, so okay, till this part it is clear.
Yes.
Yes. So now can you give me the answer for the assembled stiffness matrix? I will just wait for 2 minutes for the assembled stiffness matrix. Assemble stiffness matrix. We have discussed in detail on how to find the assembled stiffness matrix in the last class. So that is the reason I would like to wait and get the answers from you. Okay. These are the. Can we zoom out? Why can't we zoom out? Can we see? Okay, I'll hold it. Why can't we zoom out? No, I can't. I don't think we can zoom out. I'll just write K1 and K2. 1 3 minus 1 3. Yes. So these are the two matrices. I'll write the degrees of freedom 6 3 5 2 6 3 5 2 5 2 4 1 5 2 4 1. Okay. Please find out the global assembled stiffness matrix and write it down in your copies. Then we can just jot down the answers from you. Have we got the answer?
Yes, sir. Whether you can check it.
Okay, okay, yeah, sure. Thank you. Please tell the first row, values for the first row.
24,
24, correct.
12, 0,
12, correct. 0, correct.
minus 12, 12,
Minus
0,
12, 12, 0. Correct, correct. Absolutely correct. Second row,
12, 6,
12.
6,
12, then
36,
36, yeah, correct. 6,
minus 12, 9, 3,
sure, 9, 3, correct, yeah. Then
0, 6, 12,
0, 6, 12.
0, minus 3, 3,
Perfect, yes, correct. Then,
minus 12, minus 12, 0,
yes, minus 12, minus 12, 0,
8, minus 8, 0,
8, minus 8, 0. Perfect, yes.
12, 9, minus 3,
9, minus 3, minus
minus
8,
8, 9,
9, minus 1, right?
0, 3, 3,
3, 3.
0, minus 1, 1.
Perfect. Thank you, Mr. Sudhakaran. Thank you for
Thank
solving it. Um, Mr. Prabhakar, is there any problem with this? I guess it is okay, right?
Yeah, that's fine. I was in the fourth row. I was slightly slow. I was in the
Okay,
fourth row.
okay, no
That's
problem.
fine. All the four rows are fine. Yes.
Okay, 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 no problem. So we only need the four rows itself. So now what we do is we partition the matrix like this, because we need the first and second unknown degrees of freedom. Okay, so far so good, so simple. See, beam problem, it only took 10 minutes till far, so far. Now comes the interesting part. So how do you decide the loads on the beam? The loads meaning this, where is,
Equivalent joint loads.
yeah, this pk and p unknown.
This is where some confusion. Okay, we'll discuss later. Yeah.
Okay, okay. So this is the most like challenging part of the beam problem. Otherwise, so far what we have done, it is pretty simple and straightforward to the truss problem. Okay. So once we have, so this is I guess this is kind of advantage of the stiffness method. Like you understand this truss problem very nicely, so you know what is assembly of matrices and how to solve and those things. So beam problem, everything becomes very easy. The only challenging part is the loads. So now in beam problem you will understand the loads very easily, and in next class in the frame problem we just merge the truss and the beam problem to make it a very large problem, to take more space and to um, kind of use more time and energy on that. But the concepts are absolutely same, so there will be no problem in understanding, there will be no challenges in that. Okay, so this is kind of nice of the stiffness methods. Like once you go on learning method by method, it becomes easier and easier. So now comes the load, very interesting part. So for the load, I have kind of chosen this kind of explanation of the loads. You can try to relate. This is our member 1, this is our member 2. So what loads we write here? Okay, okay. So now, so this is member 1, this is member 2. Okay, okay. So let us move back to the picture of member 1. This is member 1 picture, right? this one, we have degrees of freedom 6, 3, 5, 2. Okay. Okay, cool. So now we have written down the equation also. The equation for the member stiffness 1. Okay. In this equation, what we have written? We have written P6, P3, P5, P2 of member 1. Very clear. We are very clear with this. That the displacements are global, displacements are equal for each joint, but the forces here are for member 1. Similarly, P5, P2, P4, P1 for member 1. These are not of member, these are not global. Okay, I have not written member 1 here. That is wrong. Member 2 here. Okay. So what we do is we copy these two pictures. The first picture of member 1 with the degrees of freedom, second picture of member 2 with the degrees of freedom. Here we copy these two pictures and we just write the forces that we have used in the equation. What forces we have used in the equation? P6 of 1, P3 of 1, P5 of 1, P2 of 1, P5 of 2, P2 of 2, P4 of 2, P1 of 2. So far so good. So far okay. Acceptable.
Yes.
Yes. So far no problem with this. These are our forces of like member forces. Okay. Now, apart from these, what are four kind of forces in the beam problem? So in this beam, from where do we get the reactions?
Fixed end moment reactions.
Yeah, we get reactions here, we get reaction here, we get reaction here. Okay. So what could be the reactions here? Our reactions also will number it same as the degree of freedom, just to understand that in which direction and what reaction are we talking about. Okay. So these are the four reactions that we are getting on the beam, right? We understand what do we mean by reactions, right? Here,
Mm-hmm.
the external reaction forces on the beam. So these are the four reaction forces on the beam. Okay, clear? We apply that on the joint. We have R6, we have R3, we have R5, we have R4. So far okay?
Yes, sir.
So far okay. So now simply what I would say is, okay, so far okay, so far okay, so far okay. Now simply what I would say is, if you just find the equilibrium of, so these are the three joints of the beam, right? These are the three joint positions. This is A, this is B, this is C. Okay. So now your force vector, your final force vector for the corresponding to the global stiffness matrix would be the forces here. Say this is P6, this is P3, this is P5, this is P2, this is P4, this is P1. Last
Clear,
statement I am,
clear.
yeah, it is clear. Okay, so last statement I am saying that our uh, joint forces would be a equilibrium of these small forces that are there. Okay, so basically what I am trying to say is, in this case, P6 is nothing but P61 plus R6. P3 is nothing but P31 plus R3. Very good. Okay. Yes. What I am trying to say is P4 is nothing but P42 plus R4. P1 is nothing but P12 plus 0. There is no reaction in the this direction. P12 plus 0. Here I am saying P5 is nothing but P51 plus R5 plus P52. P2 is nothing but P21 plus 0 plus P22. This part it is okay. Please comment.
Yes.
Yes. So if this part is okay, then I don't think there is any confusion in the solving of the load vector.
No,
Uh,
solving the load vector is fine. The
yeah.
confusion next step,
Okay.
we are finding the unknown displacement for the equivalent joint vectors u1 u2.
Okay. Mm-hmm.
Correct? That is for your p1 p2, what you're getting in this
Mm-hmm.
equivalent joint load.
Mm-hmm. Mm-hmm.
Correct? That we are assuming that is the final answer. That is the
Yes.
final rotational slope or whatever is that u1
Yes. Yes.
u2.
Mm.
Correct?
Yes.
Then we are using that u1 u2
Mm.
to find the unknown reactions.
Okay. Done. Yes.
Whereas that unknown reaction is already there with us for a joint load vectors.
Okay. 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 Don't. Yeah. We'll get to
That is
that.
where the confusion.
Yeah.
Okay.
Yeah.
Okay. That
We'll
is the
get
next.
to that.
That's what I said is the next step. Yes.
Yeah. So far it is clear. Now can
Yes.
you say what are these P1, P61, P means, like, what are these 1 and 2 kind of variables? Like, what do they constitute?
Fixed end moments.
Fixed end moments due to the external load.
External loads. Yes.
Exactly. So if they are fixed end moments due to the external loads, there is no load on element 1.
Yeah.
Okay.
P6 will be 0. P6, P3 will be 0.
So this is 0, this is 0, this is 0, this is 0. Very good. And there are loads on the beam number 2. So what would be the loads? We will write the answer of the loads. We will write the answer of the loads in which color? Say R, black color. So if there is a beam like this, where there is, how much is the load? I'm not 5 kilonewton per meter, as I can check. Let me see. 5 kilonewton per meter. Okay, for 3 meters. So what is the fixed end moments of this beam?
WL square by 12. 9 by 12.
Okay, and direction.
Direction will be positive. P3 is positive, anti-clockwise. That is on
No,
the
you
left
just
hand side.
forget the notations now. You just tell that in the left joint This
Left joint it is positive. Left joint is positive.
positive,
Anti-clockwise.
okay, anti-clockwise moment, and
Anti-clockwise
and
moment
force.
is 545 by 12. I don't know
Okay,
what is
I'm giving you the force is the P equals to 5 into 3 by 2, 7.5. Okay, QL by 2, and moment is QL square by 12, which is how much? 3.75. 3.75, is it 3.75? Yes, 3.75. Okay, these two values I am giving you. You just tell me force in the left hand joint, downward or upward.
plus 7.5 upward. Reaction will be upward. You're talking
I'm
the equivalent joint load or the reactions?
I am talking about fixed end moments due to this load on the beam.
It is anti-clockwise, right? My plus 3.75.
Okay, fixed end moments and forces also in this load. Like equivalent for equivalent moment and forces on this beam.
Okay. Then in that case, if you're talking equivalent, it will be 7.5 downwards and minus
Yes,
3.75.
yes, yes, you are correct. So P5 of 2 is actually this one. Okay, okay. Which color? Which color? This is P5 by 2. This is P2 of 2. This is P4 of 2. This is P1 of 2. Okay. So now P5 of 2 would be how much?
It will be minus 7.5.
Exactly, minus 7.5. Mr. Sudhakaran, we agree, right?
I
Yes,
understand.
yes, yes, very right. And P2 of 2 would be,
3.75
yes, plus or minus.
It minus
plus
3.75.
Uh-huh. I got
plus
plus. Why plus?
It is
it is
clockwise
an
minus. No, no.
No, this for P2 of 2, we see the direction of the load in this picture, right? P2 of 2.
With respect to that, it is minus 3.75. It will be in the other direction.
Uh, I think there is a slight confusion. So what is happening here is we are not talking about the fixed end moments now, like the reactions. We are not talking about the reactions. We are talking about what is the equivalent load, what are the equivalent joint loads for this distributed load on the beam. So if there is a beam like this, if you have given a load on top, the equivalent joint load, the load that will get transferred to the two joints, would be downwards. Okay, the total load would be downwards. And how will be the moment? If there is UDL, the beam will try to bend like this. Okay, so if the beam tries to bend like this, then the equivalent joint moment at the two ends would be like this. Okay.
Clear.
Clear? Okay. So if
So
the
the
equivalent,
confusion, Mr. In the lecture class, what they done, I mean that is also clear.
okay.
They have taken the equivalent joint load in some direction. They have applied sigma V is equal to 0 and sigma M is equal to 0. Then they found that equivalent joint load. So automatically you'll get plus, get to
Uh,
minus, and minus will get to plus. So
okay.
that's the reason. So they have considered the fixed end moment with the actual directions, reactions,
Yes, yes, yes.
and then they equated to that the joint loads, wherein P1 becomes minus of this M.
Oh, okay, 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 okay. So,
So that is a
uh,
thing.
but like I have
It is
also
clear.
seen the video, yes, but I try to think it in this way, so this is much more realistic, I guess. So, so we are drawing the beam side by side. We are taking each component of the beam, and this is also important later on. So later on, if you are trying to find the forces induced in each member, okay, then you just use these equations, just use these equations, p6, p3, p5, whatever these equations I have mentioned. if you just use these equations in the force vector, you will get each and every reaction and the force. Okay, that is why I told that, oh, we'll come to that later. If you try to find the reaction, you have to use this equation. You cannot directly find the reaction. That's what. I think this is okay. This is like realizable. Like we have the different joints, we have the different forces in the joints, we get the equilibrium there. That's all. So anyways, so moving on. So now P4 of 2 would be again minus 7.5 because the loads at the two joints would be downwards, and P1 of 2 would be plus 3.75 because the moments would be like this, so it is already anti-clockwise in the right hand side joint. Okay, so these are the directions, and if you have any problem, you can also ask me in the next class. Please don't hesitate. We can again discuss this. This is important. Other part you can understand. You gave me the answers of the global stiffness matrix. So this part, if you have any problem, we can also again discuss. No, please don't hesitate. Anyways, so now moving on. So what are the values of different p's which we have got? So now I would write p1 equals to p12 plus 0. P1 equals to 3.75. P2 equals to p22 plus 0. P22 equals to minus 3.75. P3 equals to, are we following like how we are getting?
Yeah.
Yeah.
P3 is 0.
No, P3 is 0 plus R3. P3 equals to R3. P3 equals to this. P3 equals to 0 plus R3. Okay. Okay.
Clear. Yes.
Okay.
Yes.
Yes. Okay. P4 equals to P4 2 plus R4. So what is P4 2? Minus 7.5 plus R4. P5 equals to 0 plus P52 plus R5. Okay, P52 is minus 7.5 minus 7.5 plus R5. Okay, P6 equals to, where is P6? P6 equals to 0 plus R6. So P6 is directly equals to R6. So this is the load vector that we have. Okay, this is the load vector. So now when we calculate after getting the stiffness matrices and all, displacements and all, now we know how to get R4, R5, R3, R6. We cannot get R3, R4, R5, R6 directly. We have this in mind. Okay. So
But
moving
Mr.
on.
Banerjee, when we are
Yes.
talking P1 to P6, we are
Yes.
talking about the equivalent joint loads
Yes.
with for the external loads, correct?
Yes.
It is not the algebraic sum of the forces at the joint. We are talking the equivalent joint loads.
Yes. Equivalent joint loads.
Then
So
for the equivalent joints, we are adding the reactions.
reactions. Okay. And also the equivalent load from the beams, right?
Yes, exactly. Equivalent joint load, when you talk, okay, you take the, for the applied load. Okay, what is that equivalent joint? External load we are applying at each joint.
Okay.
But here for P5, P6, you are adding R4. If you add that R4, what happens? That becomes the algebraic sum of the force at that given point. Equivalent joint loads are different, and I don't know, this is my understanding. Probably I may be wrong.
Uh,
That is the confusion. But
yeah, please go ahead.
in class there's given only that equivalent joint load. They didn't add the reactions. But finally, when they found that P, then they call it as a P unknown, and they added these reactions.
Okay.
Finally, whatever you're doing, you'll get the same answer. I mean,
Okay.
answer will be same.
Okay.
So when we define it as an equivalent joint load, always it is for the external load. We should not add the reaction. That is my understanding. Okay, I may be wrong.
Okay, okay. So,
Answer will be same.
yeah,
You are
yeah,
going
yeah.
to get
I
that
understand.
answer.
So, say uh, this is the new problem that we are trying to solve. So, this is the load on the beam, and we have a load like this. Okay. So what would be the equivalent joint load and at this point, at this B? This is A, B, C. What would be the equivalent joint load at B? Will we not consider the vertical force from the top?
Vertical force I'll consider, not the reactions. See, your R4, R2, what you're adding on the left-hand side in the problem, that is the reactions.
Okay. So this vertical force, if it is say P, then you will consider that.
Yes, yes.
So this vertical
Because this is
force is
external applied load.
external applied load. Yeah, perfect. Yeah, external applied load. But this P equals to minus R5, right?
Okay, logic is okay.
Huh? No, P. This
Agreed.
P. What does this roller do actually? This roller, what does this do? This roller
It
gives
is
you a
applying the load in minus direction. It is applying the
yes,
load in minus direction. Agreed.
yes. It is actually applying a load. It has some different purpose. It has a purpose to hold it in place. So,
Acknowledge.
but it is actually applying a load to that joint from the opposite direction. So I cannot visualize why we will not consider this in the equivalent joint load. And also I think this is also a part of like the definition of the beam with consideration to the um, features of the beam, like the boundary conditions of the beam. So when we are actually doing this global stiffness matrix, and then we are kind of making all the displacements at these last four joints as zero. So when we are doing the displacement as zero to make it consistent with the boundary condition, we should also take the effect of the reactions to make it consistent with the boundary conditions, don't you think?
No, that is clear boundary
Mm-hmm.
condition. See, my question is,
Mm-hmm.
see, P3, P4, P5, P6, if you find that R3, R4, R5, you'll get the final reactions with your P unknown equations or whatever is that, correct? In the final
Okay.
matrix,
Hmm.
correct?
Mm-hmm.
But if you apply that same logic, P1, P2 is not the actual moment. Moment will be zero there, correct?
P1, P2.
His moment is zero, right? That is a hinge.
Okay. P1, P2. P1,
P1,
P2.
P2 is zero, that moment.
Just 1 second. Hmm. No, 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 no.
Why? P1 is, I mean, it's a roller end, right? Moment will be zero there. It's
No.
a, see, you're applying the
Ah.
load, you're taking the equivalent joint load. That I understand. It's a fixed end
Yes,
moment
yes, yes, yes. Okay,
for that.
okay. Yeah. So, mm, so in that logic, if say P1 equals to 0, so does that mean that P4 equals to only R4, only the reaction force? P4 should also not have this vertical equivalent load, right?
P4, we are going to find it at the end, reactions.
Oh,
Using this,
so if we are say we are just you are just considering the total final force that is acting on this one.
yes, yes.
Yes. So then we consider that the moment is 0, P1 2 is 0. So the final force at this point is also P4 is the R4, the reaction force. Directly the R4, not the equivalent joint load.
so some confusion. I mean, that's see. If you say again, I'll go back to my logic. I mean,
Okay.
with this P1, P2, P3, P4 last. Hope I'll take another only 5 minutes. Hope I'll not
No, no,
be
no. It's
stretching.
fine. It's fine. Hmm.
I mean, that is the confusion. What last week also I raised that point. This is the
Hmm.
confusion in that beam problem. It is not in the truss.
Yes, yes,
Go
yes,
to
yes.
that last step, that P1, P2, P3, P4. What you?
This
Yeah,
one.
here
Hmm. Hmm.
in this, if you find that R3, R4, R5, R6, if you write that in your final global stiffness matrix or that equations,
Hmm.
definitely P3, P4, P5, 6 will be unknown because we don't know that R3, R4, R5, R6 in that.
Okay, I understand. Okay.
Correct?
Hmm.
So with that equation, you'll be finding that R3, R4, R5 and you'll be adding to that 7.5, 7.4 that you'll get that. So finally P3, P4, P5, P6 will be the final forces.
Okay. Okay.
Correct? My
Yes.
thing is correct?
Yes. Yes. Yes.
Correct? That is the final
Yes.
forces.
Hmm. Hmm.
If that is the final force, I cannot assume P1, P2 as the final forces in that beam. That is zero for me. P1 is zero because
Okay.
it's a fixed end moment.
Yes. Okay. Okay. Hmm.
Correct.
Hmm.
You are
Hmm.
treating P3, P4, P5, 6
Hmm. Hmm.
unknown
Hmm. Yes. Yes. Yes.
and
Absolutely.
P1,
Yes.
P2 is known.
Yes. Yes. Yes.
That that statement, I mean, slightly difficult to because P1,
Hmm.
P2 known means P1, P2 is zero for me on the roller
Yes.
end.
Yes. 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 Absolutely. Hmm.
Probably the logic, probably I don't know what I'm.
So.
If you apply that 3.75 moment, this is the rotations what you are getting at that end.
Yes.
Probably that is the logic.
So I.
Though force is less, if
Hmm.
you apply that moment to get that rotation, you have to apply this moment at that end.
Very
Probably
nice.
that I'm trying to
Uh, okay. Yes.
understand that logic quite. I mean,
Yes.
slightly difficult to.
Yes. 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 So, so I felt that you have very like categorically, very nicely explained step by step. You have given the answer to your own question. So you told that let us assume that P3, P4, P5, P6 would be the unknown reactions.
Correct.
R3, R4, R5, R6. Okay, that's fine. We will assume that these are the unknown reactions. So in that logic, you feel that P1, P2 should be zero.
Definitely yes. Okay, that is
Definitely.
the final.
Yes.
Yes.
So if you do that, if you do that, would you find the unknown
No,
displacement?
no. We cannot find that.
Yeah.
So that is
You.
what I'm assuming.
Yeah.
For that fixed moment, whatever the slope comes, we are releasing that moment and we are getting that rotations at that for the known unknown displacement.
Yes. Okay.
P1,
Yes.
P2.
Hmm.
It's like difficult to understand that.
Okay. So now like we have come to a conclusion that if we only take the effect of the external reactions and the point
Exactly.
external
Yes.
features of the beam without considering the effect of the load, we cannot find the unknown displacements, right?
No, what happens with your equations R1, R2, we can easily visualize
Hmm.
P3, P4, P5, 6 are unknown because we got some R3, R4, R5, 6 there
Hmm.
when we
Hmm.
are doing the matrix partition because
Hmm.
clearly it says that we don't know these values.
Hmm. Hmm. Okay. Yes.
As per the class, I mean, videos, whatever is that, they're not added this R4, R5, R6. Okay.
Hmm.
They
Hmm.
simply written P1, P2, P3, P4, P5, P6. All that has got a values there, fixed end moments.
Okay.
That is where the confusion. How it
Hmm.
is known,
So
why it is unknown there.
yes, so
Okay.
all that whatever values they have, that is actually this one, right? This value.
Yes.
Yes.
3.75, 3.75,
Hmm.
0, minus 7.5, minus 7.5, and 0 in the
Yes.
class lecture.
Yes. 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 So.
After
Huh.
finding that known displacement,
Hmm.
using that,
Hmm.
they again found this P3, P4, P6,
Hmm.
and finally they added to this 0, minus 7.5, minus 7.5. Answer is same. That's the reason I said your answer will be same.
Yes. Yes.
Understanding that logic will be quite something confusing. That is the.
Okay. Yes. Yes. So okay, like we are not worrying about the answer. Just let us visualize the problem. So if we only consider the R5, like the like here whatever P3, P4, P5, P6 we have, if we try to make that those as the unknowns, the unknown reactions, So in that case, we know that P1, P2 would be 0 because there is no unknown reaction there.
Mhm.
So that is 0, so we cannot then solve the problem. The reason we cannot solve the problem is we are actually using the stiffness method to solve the beam node by node. Okay, so when we go to node by node and we only take the effect of the external factors to the nodes and not take the effect of the load on the beam, or loads distributed over the beam, or loads applied on the beam as the fixed and equivalent loads, if we don't consider that, so our problem does not have enough information to give us the answer. Because what is happening is, say, just for example, right now we have two conditions, this one, and we have one more condition. Okay, so if we know that this is R5, this is R4, this is R6, and this is R3. Okay, similar here. Okay, so if we find our load vector to be, forget about our P1 and P2, if we make our load vector to be R4, R5, R3, R4, R5, R6, if we make our load vector to this, say, for the global stiffness matrix into the displacement vector, okay, you understand. So if we make our load vector this, so can you distinguish between these two cases if our load vector is this? In both cases these are R4, R5.
No, sorry, I didn't. I was thinking something else.
Yeah, no,
So I
no
didn't.
problem. I'll repeat myself. Yeah. So this is, say, you have condition 1, you have condition 2. Okay. And
Hmm?
we are planning to write the load vector as R3, R4, R5, R6, the unknown reactions.
Hmm?
Now, from both the conditions 1 and 2, can we distinguish between the load vector now? Leave out R1 and R2. Just forget about that. Like in these two cases, is there any difference on the equation of the beam?
No, no, there won't be.
There won't be any difference. But
No.
in the second case, the u would be 0. And in the first case, u would not be 0. There is some uh, there is some displacement, rotation, anything.
Exactly. Yes. Yes.
Yes. So now, if we don't distinguish between the load vector, how will we get the difference between the two kinds of beams? That is what I am trying to say. So in my opinion, for the timing, if we just focus on whatever we have discussed today, so in my opinion, I think we should add the equivalent loads on the joints to find out the total final, what is the load final, what is the joint load, adding the equivalent loads and the reactions.
Reactions. Okay.
Yes, so that would
So
be a proper
then,
definition of this unique beam problem.
okay, then in the final equations, you are going to get that R3, R4, R5, R6. That is the
Yes,
reaction.
yes,
And then using that R3, R4, R6, we need to find this again P1, P2 for to draw the bending moment diagram. We cannot
yes,
directly use this P1, P2.
yes, of course, that is different. Yeah,
Correct? Because
yes.
P2,
For bending moment, again, you have to do different things. For bending moment, you have
we
to
use that
find the.
R3, R4, R6 and
Hmm.
use that
Hmm.
and find the bending moment at each
Yes.
locations
Hmm. Hmm.
based on
Hmm.
that reactions.
Hmm.
Okay. So then only we'll get that P1 as 0. Otherwise, if you read that 3.75, because there are no forces on the left side,
Yes.
so bending moment will be 0 there at
Yeah.
that point.
Yes. So basically, what I am trying to say is, if we don't distinguish between the load vector in this equation, in this stiffness equation, say, if we don't distinguish between the load vector and the reaction vector, then you will not get the full unique solution for the beam. So that is what my point is, and that is why I have written the force vector like this.
No, that makes sense. Adding that R3, R5, R6, because we know that that is unknown, known and
Yes.
unknown, so that makes sense. Okay.
So
So
I
that
hope.
doesn't mean that P1, P2 is a known. P1, P2 is again it is a fixed end moments only. Using this
Yes.
R3, R4, R6, we need to find that P1 and P2 using these
Yes.
reactions.
Yes. Yes. Yes.
You cannot directly take that P1, P2 as per this vector
Yes.
again.
Yes. Yes.
I think that makes sense. Okay.
So maybe this has cleared the confusion there.
Sorry, I think I took a lot of your time there in this
No, no, no
discussion.
problem. My time is always there. Yeah.
See, initially that's what I said. You'll get the both the answer will be same. Only the methodology and understanding that thing
Uh,
is like.
yeah. Answer will be same, but I think yeah, like
See, what happens if you
understanding is
don't
more important.
understand the concept, you'll blindly do the step by step to use that,
Mm-hmm.
add that, and find that. You'll not understand that clearly why we are.
Yeah. If you just blindly try to do that, and then you just add some random load on this one, first one, and then you will you will be at fault then. Like you'll,
Confusion started there only. So in class they said
yes,
that P1,
in
P2,
this,
P3, P4, P5, 6. We
yes,
know all the values. They are
yeah,
partitioning it. This is unknown, that is known.
yes.
And then in knowing the known force, we are finding the displacement. And after finding the displacement, we are again finding the unknown forces.
Mm-hmm.
And got confused. Okay, unknown forces, we already have a number P3, P4, P5, P6. Why are we calling it as unknown in that?
Mm-hmm.
So if you add this R4, R3, R5, it makes sense because those R3, R5 will be unknown in that matrix. So
Yes.
it makes.
Okay, okay. So then let's stop here, and then in
Yes,
next
yes.
class we'll solve it in a few minutes and move ahead to the frame problem.
Yeah, then it is straightforward. We have to use that
Yeah, then
equation. We
it
have to
is
add that
straightforward.
values.
Yeah.
Thanks, Mr.
Yeah.
Banerjee. Thanks. Bye. Good night.
Okay. Yeah. No problem. So let's end the class here. And any suggestions for next class? Maybe. No, nothing.
No, I don't think.
Okay. Okay, no problem. So
Fine,
let's
thanks. If
end the
anything is
class.
there, I'll put a mail, manager. If I
Yeah,
get anything, I'll put a mail on that. Okay, thanks.
Sure. I would love that. Yeah, and
Thanks.
I would mention it again that you are a really important factor for the success of the classes.
Oh no, not like. I am learning.
Yeah. Otherwise, like it is very like difficult to just solve problems with nobody at the other end.
It is good that you are trying to answer my stupid questions. But anyway, because as I
They are
said,
they are
I
not
mean,
stupid at all. Like I feel that.
and that long back. Going back to the basics, understanding. Okay,
Hmm.
it takes some
Yes.
time.
No. I don't think they are stupid at all. They are like very insightful questions, and people actually find themselves in fault in these type of situations.
Otherwise, what happens?
The
Simply they'll
directions and
follow
those things.
the steps. Okay, keep this as
No.
unknown, keep this known, replace this value, find the. That doesn't make sense.
Yeah.
That's what.
And moreover, like you will never solve any problem by hand in matrix method. Like you will always give some feedback. You will input something in the computer and you will get the results. But like to understand the steps and the different features involved, that is I think more important.
Yeah. Yep.
Okay.
Okay.
Yeah.
Thanks,
Okay.
Mr. Bennett. Thanks.
Yeah.
Bye. Good night.
Okay. Good night. See you in the next class.